Okay, hello everybody. So this is going to be section 7.7, approximate integration when it comes to it. So a little precursor back into calculus, right, when it comes to it. So we're going to talk a little bit of a review next time, but this time we're going to talk about one section before, what approximations can come to it. So different types of ways of solving for curves underneath it when it comes to the areas, besides using Riemann sums. So last time we talked about Riemann sums is the left Riemann sum, right Riemann sum, and also the middle Riemann sum. And this was a big thing when it came to the first part of the calculus, right? Finding left and right Riemann sums. So a quick little recap. Right, let's say if we have this curve here. So the definition of a left Riemann sum is the left side of this rectangle would actually hit the curve itself. So approximation, the left Riemann sum looks something like this. In that format there. Okay. So now the right Riemann sum is just the opposite. So when it comes to the curve, it actually hits the right side of the rectangle. So kind of like this happening. Right, it comes to that. Now the midpoint Riemann sum is a little bit more complicated how it goes, because now it's saying on the curve it's actually going to hit the middle of the rectangle. So that's a little bit harder to look at. Well, let's say like this point here will kind of look like this. So if this is the midpoint, here's our rectangle in both directions. So as you can see, it's a little bit more accurate as we go along. The reason why it's a little bit more accurate, as I say, is because if you notice, right, I'm missing this piece, but it kind of substitutes with that piece there, and vice versa as you go along this entire curve when it comes to it. So you get a lot more accurate interpretation of what the actual area is underneath the curve itself. And that's how we're going to start off today's lesson, is finding the midpoint Riemann sum itself. Now, again, right, we talked about curves, so this is technically the integral from a to b of the function, or just the m sub n term is equal to its experiencing, right? If we don't know how to integrate, we use the equation when it comes to finding the areas underneath the curves with the rectangles, or delta x is equal to the sum of all the functions at that particular point itself. Okay. Well, delta f is equal to b minus a over n, where n is the total number of rectangles we're using with when it comes to it. And again, like I said earlier, each x is actually the midpoint of each individual rectangle when it comes to it. All right. Now that's one way to do it. More alternative ways, and we'll do an example of this later on, is something called the trapezoidal rule. So the trapezoidal rule says, well, you don't actually have to use rectangles, believe it or not. You can actually use different types of polygons to identify the actual area underneath a curve. Now, one of the most popular ones is rectangles, but we can also use any type of ones, especially trapezoidal rules. Okay, so a trapezoid, if you're not sure what a trapezoid looks like, kind of looks like this, where it's two parallel parts, and then one you usually have a base that's a 90-degree angle and the slanted line like this. Now, if you want, you can make it far more detailed so you can see what an actual trapezoid looks like. So you have right angles everywhere. So it's very similar to an actual rectangle, right? So the process here is it kind of look like this, as here, there, and like that. So you have areas underneath the curve here. And again, these are all trapezoidals to estimate the areas underneath the curve itself. Okay? Now the trapezoidal rule is a little different than the midpoints or the left Riemann sums and right Riemann sums in general. Is again, right, we have to go by the area of a trapezoid, right? So area of a trapezoid is 1/2 the two bases addition of two bases times the height, right? So it's kind of similar to a triangle. Same thing applies here, right? Well, delta x is, the change of the trapezoid, in this case, divided by 2. That's the equation of the area of a trapezoid, times the sum. Now, this is what you got to be very careful of, is notice it's the first one, and then each one afterwards is always 2 times it, and thus you have the last one. So it's the first and the last are not included, but in between, those functions are going to be multiplied by 2 itself. Okay? Or again, delta x is the change, so the change from b to a over the n, how many trapezoids we actually want. And again, x, and this is the key part, where x of naught and s of n are the left side of the trapezoid. So the left side meaning these ones right here, the left side of the trapezoids. Now, if you're wondering, holy moly, how do I figure those out? It's actually not that bad. It's each trapezoidal, when it comes to it, is equal to a plus n times delta x. To make it more easier to find those left sides of it. Okay, where again a is where the starting point is, right? And then delta x is again calculated here. Okay, and then n is how many trapezoids you want, n through 5 or so forth like that when it comes to it. Okay. But again, right, this is a lot of theory behind this kind of concept. So let's actually put this to practice to see how this is going to go about itself. Okay. So given the example here, we want to use the midpoint and trapezoidal rule with n equaling 8 to find the integral of this one here. Okay. All right. So let's just first start with the midpoint rule. So we'll just put that there as we go along to this portion. Let's call that A. So we're going to find the midpoint. So we have n triangles, right, when it comes to it. So we're going to go from 0 to 2. So essentially, we're going to go cut these into 8 parts. That's essentially what we want to do when it comes to it. So, cut this in, if it's easier, just divide this by 8 parts. That's 1/4 itself. So, using our midpoint formula, we go from 0, 1/4, 2/4, 3/4, all the way to the, to 2 itself. And that is 2 itself, right? We go from 0 to 2, broken up into 8 rectangles themselves. Okay. Now, here's the problem. So these only represent the spaces between them. However, I want the midpoint because we know the midpoint of each case is going to be what we want because we want the midpoint Riemann sum, not the left itself, left or right, based off that, right? So what's in between 0 and 1/4? Well, that's 1/8. What's between here? That's going to be 3/8, and so forth down the line. So notice everything is literally just cut in half when it comes to it. Okay. So in that case, when we want to find the midpoint Riemann sum, it's going to be delta x, so it's going to be 2 minus 0 over n, which is 8, times the function, the function at each midpoint itself, so f of 1/8 plus f of 3/8 plus s of 5/8, and so forth down the line. And there we go. And now we just plug them in, right? So in this case, we plug in 1/8 into here and see what we get out. So, for example, this is going to be 1/4. And I'll do a couple of them so you can see how that's going to go about. And just straight out, using a calculator at this point to figure those ones out itself. So if you plugged in 1/8 into there, and you round it 2 decimal places, you just get 1, because I think you get 0.99 something. Plug in 3/8 into our function, and you get roughly a 0.997, and you can keep going. Okay? And then finally adding all of this up and then dividing by 4, and we get our area, or approximate area, using the midpoint Riemann sum of about 1.041. And there we go. And again, that's using the midpoint formula. So to do the trapezoidal rule, again, we're just going to follow this template. Very similar, right, when n equals 8 itself. Okay? So for the trapezoidal, so we already know what delta x is, right? Delta x is here is 1/4. However, we have to divide it by 2, so just a quick little algebra portion, right? 1/4 divided by 2 is 1/8 this time. So we know it's going to be, is it Tn? So T of 8 in this case is going to be 1/8 times, and then this is how we're going to follow this template here. Okay, so first it's going to be f of 0, right? That's our first term, plus f of, now if you didn't know how to do this process, right? If you were just doing, the old-fashioned way, using the equation, well, here in this case, let's say we want to find x of 1 because we found x of 0 already, or x of 1, right? So a is 0 plus 1 times the change of this. So this is 1/4. And there you go. So that is 1/4. You want to find x of 2, which is going to be our second term here. You do the same thing. So 0 plus 2 times, because you want, now it's the second trapezoidal, and this gives you 2/4. So notice you see, same process when it comes to it, and it gives you roughly the same thing here. So we only, again, be careful. It's going to be 2 times it. This is going to be f of now 1/2. That's 2/4 plus 2 times the same thing. If this is going to be 3, this is now 3/4, and just keep going down.